Hello and welcome to the first class in ME236, Thermodynamics 1. This is the introduction, and we're going to be sticking close to the book, the textbook. Oh, here's a place where I tell you how to make an A. And I think I've already talked about this in class. You need to buy the book. The book is your lifeline. I'm not going to be able to spoon feed you everything out of the book, so you're going to have to read it, work through it, and I highly recommend that you scan the book. You don't have to read it in detail before class, but before each topic, I think it's a really good idea to look at the pictures, look at the different headings, maybe read a little bit, not much. I mean, you don't have to spend more than about 5 minutes maybe in order to get a lot of benefit before class and get a lot out. And then as you go and do homework assignments, make sure that you're looking back through the examples and through the different sections, at the main equations and all the stuff around it, kind of understanding what the context is of how to use the equations. Make sure you come to class. That's really important. I mean, well, that's what we're here for. And when you're in class, ask questions. Reading the book ahead of time will help you think up some questions, maybe things that you didn't quite understand of the small amount that you read, or figures and that kind of thing. Take notes. I prepared these notes that I'll show you as I use them. I think they will make things faster to take notes. And I'd also mention that you should probably jot things down that you're wondering and thinking during class, so that you can interact in class and stay engaged. Don't be passive. You don't really get a lot out of class if you just sit and listen. When you do the homework assignments, make sure you're trying to do it yourself until you absolutely need help. Help is out there. I will help. You maybe get a classmate to tutor you if you're really struggling. Maybe go to the Center for Student Success and look for tutors if that's necessary. I believe Dr. Milanovic might have some type of tutoring session that's going on in the library. I forgot to mention that in class. So if you happen to watch this, remind me, please, that in case I don't remember. Yeah, definitely come ask for help. I have my office hours are the best I can do to try to make them available to everybody. But if you have class during my office hours, make sure you send me an email. Ask me for questions. I can meet with you over Collaborate, or we can set up a different appointment. And practice solving problems before exams. Don't read solutions to problems as the main or only thing that you do before an exam. If you have to actually exercise your brain, simulate the exam as best you can, and challenge yourself to solve problems, and you'll be way more prepared than if you've just looked over what's already been done. Don't attempt to memorize things as much as maybe that you've done in the past. You have to change your exam preparation habits for college, especially as you progress up higher and higher from freshman to sophomore to junior to senior. It's just part of the process. So let's see. There's my schedule. We already covered all this in class. The syllabus. These are available on Blackboard to read in detail. I've talked about them. So let's get to it. All right. Oh, and then these are the notes for today, these handout notes. And if this is on YouTube and you want to get access to these, I'm sorry, I'm not making them available. So please don't ask. All right, so here's the introduction to thermodynamics. I think it's a good place to start. Thermodynamics, the therm part of it is heat, and the O is just because that's a fun letter to stick in the middle of things. And dynamics, it means movement, right? Motion. So we have heat, motion, and heat is moving from one thing to another. And here's a great example, because here's a fairly complex power plant, a coal-burning power plant. Coal isn't the most popular thing, I think. We also have oil right in here to augment it right there. So it'd be like diesel or whatever. But we heat up this water and turn it into steam. So there's water along these sides. These are tubes. And that heat transfer goes up to a steam drum where it's half full of the gas phase of steam and half full of the liquid phase of steam. And I know that sounds like a strange thing, but there's a water steam mix until you put it through a superheater. But let's just say that this is a wet steam plant where we're just going to use non-superheated steam, and it goes to a turbine, and that turbine converts this heat energy into rotational energy, and then this generator turns that rotational energy into electrical energy. But that steam still it hasn't completely turned to water yet. It still is partially steam, and it comes down into a condenser, this heat exchanger, where it takes out the latent heat of vaporization and turns it back into water, and a pump pressurizes it, and it goes back into the boiler. And we have ourselves a loop, and that loop is considered a cycle, right? So here are the note sheets. So what I would draw on here is a cycle, and we call this a closed cycle. And in many different, of course, so we could also take a look at here's an open cycle, sort of a weird open cycle, but let's call it anyway. We have the potential energy of the coal, the chemical potential energy of coal, and it's ignited and released, and it goes up into the stack. And because coal is kind of dirty, we go into this cleaner where it takes out the ash and some other things that can take place and get out of the particulates and all kinds of different things as best we can. We can even put some chemicals in there and remove some of the sulfur and other things that we don't want out, and then we can release it up. So this is sort of an open cycle, if you will. Not a perfect open cycle, but it's sort of an open cycle. So we have closed cycles and we have open cycles, right? And these things would happen right here. We also have another. You can see often you can see that this might be not really on a ship. This would be seawater coming through here to cool down this, but we could also have like a cooling tower. So that could also be sort of another type of cycle that's going on, where we're spraying a mist of water and using the latent heat of vaporization of that to cool down the liquid. I'm trying to get the right word for it. For the operating fluid that's going on inside the steam plant. So there's a bunch of different cycles happening right here. So in Thermo 2, we were going to be doing a lot more cycles. We'll look a lot the things that we need to know in order to do that. We will talk about cycles. But also what takes place here is we have different processes. These cycles are made up of processes. Like there's a process between coming into the turbine and coming out of the turbine. And in a perfect world, this would be a isentropic process where we have work produced here. All right, so I already did that, so leave me alone. And then also from this point to this point, we have a heat rejection process that's taking place through the condenser. Across the pump, we have a small amount of energy, but it increases a pressure between these 2 points. And the type of process that's taking place there we'll explore. And then we have a process between here and here where there's heat addition. So many times what we're trying to do is break down a complex piece of equipment into a cycle, and those cycles made into individual processes and what happens between there. So that's like the main mindset. We also have that's just a steam plant. There's many other kinds of plants or things that we might look on. Here's a refrigerator, and once again we have a process this is a cycle. And once again we have a cycle looking at over on this page where we're coming around here, right? So that cycle, it repeats itself, and this is also a closed cycle, and we're using refrigerant inside here. Most often it's appropriate to start with the compressor where we're adding work, and that work results in a higher pressure. So we have a high pressure and high temperature in the process. The pressure and the temperature go up across the compressor, and then across the condenser we have a process that goes between here and here that removes heat, and the heat goes to the room. And now we have a high pressure but lower temperature refrigerant, and we go across this expansion valve. And this expansion valve, what it does is, because it's high pressure, it drops the pressure across here, and in the process, because of the nature of the refrigerant, it drops in temperature, right? And then with that, and in that process, and because it has to drop in temperatures, as really cold, it needs heat, and so it removes heat from the inside of the refrigerator, and we come back and it goes back into the compressor. So we have a cycle right here, but it's all broken down between processes. There's a process between here and here, a process between here and here, and a process between here and here, and then again a process between here and here in the evaporator. So we could keep going on this. There's lots of different engines and pieces of equipment where we're able to break down the way that they work. And one of the main ways that we do this, of course, I'm really just introducing some of this information. We're going to be using it later, so you'll get more comfort with it. You don't have to memorize it now. This is sort of our introduction to it. A lot of times what we'll do is we'll define a control surface around a control volume, and then we'll look for things that are passing in and out of the control volume. So look for that. Quite often it could be a mass flow that has properties here, and a mass flow that has properties here. We will also consider there has to be the conservation of mass. What comes in must come out. We also see that though that heat might transfer or work might transfer in other means into or out of. Whoops, I was writing onto this thing and I wasn't showing the camera right here. So we've got this control surface or maybe control volume, and we might have mass coming in here and mass coming out there for the conservation of mass. And then also in this control volume, we might have heat as it escapes maybe from this compressor. Maybe it's, maybe not a lot, but this thing is getting hot, so it's gonna come out of there. And the shaft is crossing this boundary, so there's work being put into there. We could also define the control volume. Actually, usually we make it with a dash line, and maybe keep this in here, but instead we might have the electrical power, right? And as a mechanical engineer, I'm afraid of electricity, but we will have, there's electrical energy now crossing that boundary. We have a choice of how we draw that control volume and the made out of control surfaces. Sometimes we might want to zoom into something, right? This is more of a system perspective. Well, let me take that back. We use the word system quite often in synonymous with a particular grouping of mass. So that's a nomenclature type of thing. And so we'll draw the system boundary, and of course this gas gets smaller. So this system and its boundary, it can move. We can also have a control volume that gets smaller. But this is a particular mass, whereas this is a particular location, and this mass can come in and this mass can come out. So there's a little bit of a difference between the system perspective and the control volume perspective. And when we get to fluid mechanics, that's an important type of distinction. So it's something that we want to introduce here and go from there. All right. So we want to talk about the macroscopic versus microscopic point of view, the perspective. So in the chemistry, they will have a class often called thermodynamics, and the difference here is we're not really going to be focusing so much on zooming in and taking a look at what's happening to the molecules. We're more interested in taking a step back and looking at the macroscopic perspective. We can take a little chunk of fluid or what have you and analyze it, but we're not looking it down at the molecular level. So, but if we were to look at the microscopic level, we would see how these molecules bond to each other, and for instance, in the different phases, where we'd have a solid or a liquid or a gas. And it's good to think in those terms when trying to analyze things. Recognize that the amount of energy that's taking place between these two phases, right? Where there's a strong bonds between the molecules in a solid, whereas there's looser bonds and movement between the molecules. They can move, they're not attached to each other, but they kind of stick to each other a little bit. There's some stickiness, but there's movement taking place. Whereas when we have a gas, they're bouncing off of each other like crazy, and there's large spaces in between these molecules. So gases have a much larger volume for a particular mass than the liquid phase of them. And sometimes, not always, there's a little bit of change in volume between the liquid and the solid phase. Sometimes it can even be I think with water, it actually gets its densest right around like 4 degrees Celsius, and then it goes back to be less dense. So the ice is less dense than the liquid, and therefore ice floats. Talking about the definitions of some of these words, we just mentioned phases. I don't know how much more I want to write in my notes about this. And by the way, you didn't see that I left a place blank right here, and I didn't write down everything I write down in this place. This is not a fill in the blank note sheet. This is a skeleton. So write things that mean something to you, things that I say, or things that occur to you, things that you want to know, or leave it blank. I don't care. I often, by the way, I've left the boundaries here. These side little things, they actually have a purpose. And I want to have you write stuff later on, or it could be in class. It's up to you. And quite often, I will have other colored pens and things that I will write notes to myself in these borders, or maybe write the page number in the book. Remember that you want to be using the book in conjunction with these items right here. This is where I should probably first point out that these figures come from our textbook, Bornacki. I don't know how to pronounce it, but I think that's it. There's also some from Sengel, right? So these are two different textbooks. They're both very good books. So coming back to what we were talking about, and notice that this is the section, right? You want to go to the book and look up this stuff, because I'm not going to tell you everything that you need to know. If I happen to skip over something and you want a complete set of notes, go to this section, read or scan through, and write down what you want to remember in this, in your exam preparation, or in your post-class type of work. So for phases, we've already kind of talked about it here, where we had the solid and liquid and the gas. And for that, it's like the example, of course, we all think about is ice, water, and steam, right? But you can also have other things, right? You've seen that you have liquid nitrogen, right? So again, really, really, really cool. If you go really, really cool, it'll become a solid. I'm pretty sure. I've never actually seen it. Or if you've seen, ever seen the movie Real Genius? Go look up Real Genius. It's not a great movie, but it's from the 80s, and I liked it. And a house explodes because it has popcorn. They put a lot of popcorn in. Space lasers make the house explode due to popcorn. And so I think that's probably a pretty good advertisement for that movie. But anyway, they use they cut a little piece of solid nitrogen. I think, I don't remember. We'll have to look it up again. You do your research. Go look at that movie. States. All right, so we use this phrase states, and it's kind of an important thing. We'll see on the next page where we're trying to get the idea of states. But it's usually the condition, right? And that doesn't really define it all that much, I recognize. But it's a condition based on pressure, temperature, and then it could be several other things, but I will often go, let's just call it density from now on, for the time being, I'm sorry. Density, which we will soon discover, we don't really look at density as often. We start thinking about density as the inverse of density, which is 1 over density is equal to 1 over specific volume. We like specific volume more when doing problems, but probably it's easier to get our head around density than it is volume. But one of the reasons why we go with specific volume is we already talked about this, so I'm not going to talk about macroscopic properties. One of the reasons why we talk about specific volume is because of the difference between intensive properties and extensive properties. And maybe I should write properties. And by the way, in your book, I think most of these words that I put down in here are in bold print, so you could read the words that are around these words to kind of get a better sense of what they are. But intensive properties are independent, dependent. Wow, that's terrible. Of mass. So that's like pressure and temperature and density. But like volume is not, right? So, so that's an extensive property. If cut in half, property changes. Property changes. And one example might be, I should write the example up here. Example might be mass. I mean, that's kind of silly, right? But if you cut the mass in half, the mass is 1/2 of what the mass was. Or you have volume. You cut the volume in half, it's half the mass, right? It's half what the thing is. So this is like, this one is what the mass matters. Up above here is mass doesn't matter. So if you divide the volume by the mass, it becomes an intensive property. So we have specific volume, which is going to be the volume per mass. That property does not change with mass. And we'll find that we do a lot of work with intensive properties. Some of the heat or work and that type of thing, instead of having it as just work, we'll have it the work energy per mass, or we'll have the heat energy per mass. So down here we might have the total of something. Here we'll just have the, you can almost think mass intensity of the property. Some by their nature though don't have that problem, because if something is a volume of pressure, you cut it in half, as long as we don't think about the leaking part, like let's put some type of like enclosure in there, in the part where we cut the thing in half, the pressure doesn't change between splitting it in half of the amount. Same thing for the temperature, same thing for the density. So it's an intensive property versus extensive property. And it's a good thing to recognize. We do a little bit of for certain things, we have a tendency to use lowercase letters for the symbols of intensive properties and uppercase letters for extensive properties. So be on the lookout for that, so you can get used to this means. Now, we had mentioned properties and finding the states. One of the reasons why I want to find the state is we could take property A and property B, and they could be temperature and pressure. Doesn't, for the time being, we'll just say these are generic, and we could find those two things, and that defines the state. And then we have another property and property, and that defines the other states. We have a state 1 and a state 2. And right here what we have is a process, right? So a process goes between two states. So that's why it's important to make this definition of the states. We find the condition of the thing from the temperature and the pressure. We can look up and say, well, that it has we've completely defined what the state is, so that we can find. And then this path right here though, this can take like weird different ways to get to these different points. So we have to define certain processes types and characterize them. Here's an example right here where we have a pressure and a volume graph, and this is very common, the pressure and the volume. And we have state 1 to state 2, right? And so here's the direction this thing is moving, and this categorizes this piston that's being moved from this position to this position. So obviously its volume got less because we're squeezing this system right here. So this is defining what's happening to what's inside the piston. And even like if we take itty bitty tiny little steps, we can and with the right kind of condition, maybe we can add heat. We could change what the process of this path is. But there is also sometimes we might insulate this type of thing, and if we insulate it like perfectly, which is not possible, we can try to make something that's called an isentropic process. It's a very important type of process, because it's a theoretical process that's in a cable. It's not possible to do, but that's it's a good starting place to see what theoretically what could happen. All right, so I'm almost done with my amount of time. That's why I need to be more efficient in my descriptions of things. I think I'm almost there. Maybe I want to cut. Now I'm going to continue a little bit further. So it took 25 minutes to do this. That's why the class time took so long. I should have recorded this video ahead of time and been a little bit more efficient. All right, so here's some examples. A very important and common example is the Brayton cycle, right? And let's see what the pretty pictures look like. Okay, it's not that prettier. It's not that much prettier. But you see, we have fresh air coming in, and the compressor increases its pressure. So we're putting some work going into this. That work is actually coming out from this turbine, right? So that's actually some of the purpose of this turbine is we can get some of the work out of the turbine to actually make the pressure go up. And now with this high pressure, we can add fuel into this combustion chamber and increase the temperature. So the temperature did increase some, but it gets a lot more high temperature in here. And now it has a lot more energy, and it goes into the turbine where we extract. Some of the work goes back into here. So there's like a little tiny mini cycle going on here. But the main thing we want is to try to get some work out here from the output. And then we also exhaust out, right? So there's going to be some heat loss because of this exhaust. And the two main types of diagrams that we look at is temperature versus entropy, which we haven't really introduced yet, but we can kind of like just be on the lookout for it, sort of foreshadowing of things to come. And then we also have a PV diagram, which is a very important diagram. But you can kind of follow this from point 1 to 2. You can see from 1 to 2, we have increased the pressure, and we've also squeezed it down, so the volume has decreased. And then we add heat in, so the pressure hasn't changed, but we have expanded it some right here. You can't see, neither of these is really a good estimation. We can't see the temperature, that the temperature has gone up. The temperature has gone up greatly between right here and here. So you can see between 2 and 3, the temperature has gone very, very high. And then we start to extract it from 3 to 4, right? So the pressure is decreasing, and now the volume is increasing. And by the way, this should be specific volume because we're doing this. You'll notice these are lowercase q's going on here and lowercase w's that are taking place there for the workout. And now it exhausts, and so this is just the heat out for the exhaust coming back from 1 to 2. And this is considered an open cycle. And then, as I described previously, another example is to be a steam plant, where we hear, now this is a closed cycle. So we have an open cycle and a closed cycle. This is called the Rankine cycle, whereas the gas turbine is the Brayton cycle. And here again, on a TS diagram, a PV diagram doesn't really do much for us. But you can see, if you just imagine what the entropy is right here. But we have a process that goes from 1 to 2. And so you see 1 to 2 is across this pump, so it's a little bit of work added in. So external work is from the shaft of the pump. And then we start to heat it up in the boiler, and for a portion of it, it's just getting it hot enough. It turns into steam underneath this dome right here. This is a properties of water dome. So the TS, this little dome thing doesn't change. It's like a kind of part of the nature of water. And as we're heating it up from a liquid and steam mixture underneath the dome, hits right here, and now it becomes pure steam. And now we keep adding heat to it in the temperature, and it gets to this one, and that's right up here, right? So we get to point 3, and then we go through a turbine and we start extracting the work out, right? So that's the work out over here, and then it comes down and it gets a little bit back into wet, and then it gets down to the condenser, where the condenser removes all of this, and all this heat right here. This is the latent heat of vaporization, and this is removing the latent heat of vaporization. I guess we could call it the latent heat of liquefaction. Sure, why not? I don't think people use that word any, but that's what we would say. So I think I'm going to end right here because this is too long of a video. But hopefully anyone might want to go a big review for the first part of the course, or if someone ever misses the first day of class and I teach this class again, this would be helpful for you. We'll see you in the next video where we're going to cover dimensions and units.